Okay, so now we understand the aspect of what does the Fourier transform tell us about the frequencies in signals and systems in terms of continuous time, in terms of the continuous time aspects. So what we now want to do is understand what about understanding discrete time signals and systems in terms of some similar transform. Previously, you were probably just studying Fourier transform, but now we'll have to make the distinction that what we talked about earlier is called continuous time Fourier transform. It's a Fourier transform for continuous time signals, because now we'll move up to the concept of discrete time Fourier transform. Okay? And we'll understand, first of all, what is the meaning of frequencies in discrete time, as there are some differences between the continuous time and discrete time frequencies. Okay, so what's the similarity between continuous and discrete time frequencies? The similarity is that frequency still means rate of change of a signal or rate of change of a quantity. Of a discrete signal or sequence. But there are some key differences in continuous time frequencies and discrete time frequencies. And they are very important for you to understand, because when we are talking about digital signal processing, all the processing is happening inside a digital system, which means that we are always dealing with discrete signals, which means we are dealing with discrete frequencies, and we need to be able to relate those discrete frequencies to the continuous world that we understand better. Okay. So what are the differences? So the first difference is that in continuous time, all frequencies are distinct. So let me explain what this means. This means that if I have two signals, x1 of t is cosine of omega 1t, and x2 of t is cosine of omega 2t, and if I tell you that omega 1 is not equal to omega 2, then this automatically implies that x1 is not equal to x2 of t. Every frequency in the continuous world is distinct. A 2 kilohertz frequency is different from a 2.0001 kilohertz frequency, or a 2 million hertz frequency, or a 2 gigahertz frequency. The second thing is that in continuous time, if a frequency omega 1 is bigger than omega 2, then this means that x1 of t fluctuates or changes faster than x2 of t. So if I have a signal with some frequency, I can always generate another signal with a higher frequency, which will change even faster. A 2 gigahertz signal changes at a slower rate than a 2.5 gigahertz signal. Now, both these things are not always true in the discrete time case. And there is a third small fact, which is that if I write x of t equal to cosine of omega t, and omega is a number between minus infinity and infinity, then this cosine is periodic. A sinusoid is always periodic in the continuous time world. Right? This is also, so x of t is periodic, but this is not true in the discrete time case. Okay. So let's first ask ourselves, what are the fundamental building blocks in the continuous time world? The building blocks of frequencies are cosine, sine, complex exponential. In the discrete time world, the building blocks are still those with a little bit of a difference. So fundamental periodic signals in the discrete time world are still, for example, cosine of little omega n. Okay. So x of n could be cosine of omega, little omega n. Now little omega is just a dummy variable. Little omega is used sometimes in notation to signify that we are talking about discrete time signals, but it's not always the case. Okay. X of n could be sine of little omega n. X of n could be e to the j little omega n. These are still the fundamental periodic signals in the discrete time case, as long as little omega can be written as 2 pi f, and f is a rational number. For example, cosine of 2 pi times, let's say, 1/2 n, right, which is cosine of pi n, this is periodic. Okay? But cosine of 2 pi times 1 over 2 pi n, which is cosine of n, this is not periodic. So this is periodic. This is not periodic. What's the definition of periodic? It's that there exists some capital N that after that the signal starts repeating itself. Right? So first of all, the fundamental periodic signals in discrete world are still cosine, sine, complex exponential, but they must be such that omega can be written in this form, 2 pi f, and f is a rational number. So I can write cosine of n as 2 pi f, but my f is 1 over 2 pi, which is not a rational number. Okay. Now you can, an easiest way to convince yourself is go into MATLAB and try to plot these things and see if you can find a, they will look periodic, but there is no single period which makes them periodic. Now, when we are talking about frequencies, the convention, as I said, is omega is often used for discrete time frequencies, and the units of little omega in the continuous world, the units were radians per second. In the discrete world, you don't have the notion of seconds. So in the discrete world, the units are radians per sample. Now, in terms of differences, as we said, the first difference from continuous time world is that not all discrete time frequencies are distinct. Rather, the discrete time frequencies are periodic. If I am given a frequency little omega 1, and I define something x1 equal to e to the j omega 1n, then a frequency omega 2 equal to omega 1 plus 2 pi k for any integer k is the same as omega 1. Discrete time frequencies are periodic themselves, and the reason for that is if you just, so let's write down x2n equals to e to the j omega 2n, and now plug in the value of omega 2n, you will get e to the j omega 1 plus 2 pi kn. Now write them down as product of two exponentials, so you get e to the j omega 1n, e to the j 2 pi kn. So e to the j omega 1n, of course this is frequency of omega 1, but what is e to the j 2 pi kn? E to the j 2 pi kn is simply, if you expand it, it's e to cosine of 2 pi kn plus j sine of 2 pi kn. So cosine of 2 pi kn is 1. It's a multiple of 2 pi, it will be 1. And sine of 2 pi kn will be 0. So you get back e to the j omega 1n, which means that x1n equals to x2n. So even though your frequency shifted by a factor of 2 pi times k, you get back the same signal as you had before. So what this means is that in continuous time frequencies, there is no such concept. In discrete time frequencies, repeat themselves after a shift of 2 pi k. Okay. And that is why, whereas continuous time frequencies, you really have to talk about every frequency from minus infinity to infinity. In the discrete time world, the convention is that you can either talk about omega from minus pi to pi or omega from 0 to 2 pi, this is the standard convention. And that is enough to know about all discrete time frequencies, because every frequency after that is just going to be a repetition of whatever was happening between minus pi and pi. So this is called fundamental discrete time frequencies. And all the frequencies after that will be the same. So in the continuous time world, there is no such notion. All frequencies are distinct. In the discrete time world, frequencies, when you shift them by a factor of 2 pi k, they become the same. So what we now want to look at is what is the meaning of low and high frequencies then in the discrete world, because the frequencies are not unique. So difference number 2, which is related to the difference number 1, we'll look at what happens as little omega goes from 0 to 2 pi. Okay, so we'll define one signal x1 of n. Let's define that to be cosine of omega 1 n, and let's restrict omega 1 n between 0 and pi. Okay, and now define another cosine x2 of n equal to cosine of omega 2n, and then define omega 2n equals to 2 pi minus omega 1. So omega 1 is between 0 and pi. This means that omega 2 is between pi and 2 pi. So omega 2 is a bigger number than omega 1. In the continuous world, if a frequency is bigger than another frequency, then that means the signal fluctuates faster, right? Now, so we clearly have that omega 2 is bigger than omega 1, but let's look at it. Expand x2 of n, that is cosine of 2 pi n minus omega 1n. Now, if I use the Euler's identity, I expand that, I'll get e to the j 2 pi n, e to the minus j omega 1 n, plus e to the minus j 2 pi n, e to the plus j omega 1 n over 2. And since e to the j 2 pi n is 1, minus 2 pi n is 1, I get, again, do the reverse Euler's identity, omega 1 equals to omega 2. Cosine of omega 2n equals cosine of omega 1n. So what happened was, if I look at frequencies little omega from 0 to 2 pi, and here is pi. My omega 1 was somewhere, so let's say this is my omega 1. My omega 1 was here, and my omega 2 is somewhere here, and there is exactly, so omega 2 is 2 pi minus omega 1, and what happened is that omega 2 is the same as this omega 1. So this is in general true. Right? You can carry that forward. What happens is that a frequency of 0 is the same as the frequency of 2 pi. So there is a wrapping around a frequency around pi. Okay? So your frequencies keep on increasing as you go from 0 to pi. But as you cross the pi region, now your signal, instead of fluctuating higher, it starts to fluctuate less. So you go up to pi, your signal is wiggling faster and faster and faster. The moment you cross pi, you are actually now going back into the 0 to pi region effectively. Right? So our frequency here is mapping here. A frequency here is mapping here, and so forth. Right? So in the discrete world, 0 is, of course, the smallest frequency. But 2 pi, multiples of that, 2 pi, minus 2 pi, 4 pi, they are all 0 frequencies actually. Okay. So 0 is the same as 0 plus minus 2 pi plus minus 4 pi and so forth. And in the discrete world, the highest frequency is pi. I'm right now only talking about the positive frequencies. It's the same in the negative side. So on the negative side, minus pi is sort of the fastest wiggling negative frequency. So in the discrete world, what happens is if I draw a plot of little omega frequencies, here is 0, here is minus pi to pi, minus 2 pi to 2 pi, and so forth. In the continuous world, we know as we go away from 0, we are going towards highest frequencies. In the discrete world, what happens is that all the frequencies around 0 and all the frequencies around 2 pi and all the frequencies around minus 2 pi and so forth, these are all low frequencies. Similarly, any frequencies around pi region are high frequencies. Pi region, minus pi region, minus 3 pi region, minus 5 pi region, and so forth. Right? So frequencies around odd multiples of pi are high frequencies. Frequencies around even multiples of pi are low frequencies. A major difference. Now let's look at why is that the case. Just a little bit intuitively, in discrete time, we said pi is the highest frequency. So let's define a signal cosine of n equal to x of n equal to cosine of pi n. So our little omega is pi, so we have the highest frequency. Now what will the signal look like? Cosine of pi n is either plus 1 or minus 1. It's plus 1 when n is even, it's minus 1 when n is odd. Right? So if you plot it, what you will get is at 0 it is 1, at 1 it is minus 1, then it is again 1, minus 1, so at 2, 3, and same in the negative direction. Now if you look at this plot, this is really for little omega equal to pi, your signal is at one time plus 1, the other time it's negative 1. So it's the fastest rate that it can wiggle. Right? Now in the continuous world, between, for example, any 2 points, you can insert another further change. But in the discrete time, I cannot define my signal further between 0 and 1. There is no point to define a signal. And so that's why in discrete time, once it goes 1 and minus 1, that's the fastest rate of change. Right? At one point it's 1, the next point it's minus 1. You can't change it faster in the discrete world. And that's why in the discrete world, intuitively, if you want to think of it, pi is the highest frequency. So that's just a description of discrete time frequencies. Now what we want to do is develop an understanding of arbitrary signals, which are not necessarily cosine or sine or complex exponentials, in terms of these frequencies. So in the continuous world, we understand that every signal can be written as a combination of infinite number of frequencies. We want to understand, is it true that in discrete time, any signal, not necessarily cosine or sine, is it true that in discrete time, any signal can be represented also as a combination of all possible frequencies between minus pi and pi? Okay. So this is true, and that's where we come up to the topic of discrete time Fourier transform, which is very similar to the concept of continuous time Fourier transform. Remember, continuous time Fourier transform is effectively a means to tell us which frequencies are present in your continuous time signal. Which continuous time frequencies are present in your continuous time signal. That's the same understanding for the discrete time Fourier transform. It's a transform of discrete time signals, and it will tell you which frequencies make up your discrete time signal. Okay? So to define discrete time Fourier transform, or as we'll call it DTFT, we have the same condition, first of all, that every finite energy signal in discrete time can be represented as a continuum of discrete time frequencies. It's exactly the same concept that we learned in continuous time. What is the definition of finite energy? That if I take my signal and I compute its absolute value and then square it, then that is less than infinity. Okay? This is the definition of finite energy. If this holds, then any signal, not necessarily sine, cosine, or complex exponential, any signal x of n, I can write that as 1 over 2 pi minus pi to pi x of e to the j omega n d omega. Now compare that to the continuous time Fourier transform formula. What this is saying is that, first of all, integration is just like summation, right? So you are saying your signal xn is made up of an infinite number of frequencies, but instead of the frequencies between minus infinity and infinity, which is the case for continuous time, now your frequencies are between minus pi and pi. So your limits of integration are between minus pi and pi. In general, they can be any 2 pi region of your frequency. Okay? And so your frequencies are given by e to the j omega 1. And how much is each frequency present? That is given by this function e to the j omega, tells us how much little omega frequency is present in x of n. So what is x of e to the j omega? First of all, let me clarify. X of e to the j omega, you could also write it as, for example, is the same as, I could write it as capital X of omega. The reason we write it as e to the big j omega is to clarify that it is the discrete time Fourier transform. Okay? The variable here is little omega. So x of e to the j omega is a complex number, and the magnitude of that complex number, I can write the x of e to the j omega in polar form, absolute value of x of e to the j omega times e to the j phase of x of e to the j omega. Right? So the magnitude of that tells me how much little omega frequency is present in my signal, and the phase of that tells me what is the phase of that frequency that is present in my signal. This x of e to the j omega, this is called discrete time Fourier transform. So this is just an intuitive understanding of what is discrete time Fourier transform, but we haven't defined the Fourier transform formula. So if I am given a signal xn, which is finite energy, then again we write its Fourier transform pair as x of e to the j omega. And the relationship is, if you want to find out which frequencies are present in the signal, you compute the discrete time Fourier transform, which is given by the formula summation n from minus infinity to infinity xn e to the minus j omega n. Okay. In the usual way of transforms, this is called the analysis equation of discrete time Fourier transform. It's called analysis equation because it helps you analyze which frequencies are present in your discrete time signal. Okay. And we already looked at the synthesis equation. If you are given the discrete time Fourier transform, then the inverse Fourier transform formula is 1 over 2 pi minus pi to pi x of e to the j omega e to the j omega n d omega. And this is called the synthesis equation because it helps you synthesize from your Fourier transform the discrete time function. Okay. Now, the important thing to note here is the following. Xn is a discrete signal. Okay. But x of e to the j omega is a continuous function of omega. So while you have a discrete signal, it is made up of an infinite number of discrete frequencies. So the discrete time Fourier transform itself is continuous. Okay. Okay, so the interpretation of discrete time Fourier transform is exactly the same as before, as in the case of continuous time Fourier transform. For example, let's say that I told you x of e to the j pi by 2 equals to 0 for some xn. What is that telling me about that signal? So if this is the case, then this means that little omega equal to pi by 2 frequency is not present in my signal. Okay. So this is sort of like Fourier transform lets me take an X-ray of my signal, where the X-ray is sort of like looking at which frequencies are present in my signal and which are not, or if they are present, how much they are present and how much they are not. So here is another example. I look at the magnitude of my Fourier transform, and I look at absolute value of e to the j 3 pi by 4, or is equal to 2, and absolute value of x of e to the j pi by 4 is equal to 4 for some xn. Right now I'm just looking at the magnitude. Right? Of course, the phase will tell me what are the phases of these frequencies, but if I look at the magnitude, what is the conclusion that I can draw from these two pieces of information? So what I will say about this is that the frequency at little omega equal to pi by 4 has double the strength of the frequency at omega equal to 3 pi by 4, and in other words, the frequency at pi by 4 has a 3 dB gain over 3 pi by 4 frequency, right? So there's a 3 dB gain. So now some facts about discrete time Fourier transform. We already looked at the first fact is, I can call it fact 1, which is that discrete time Fourier transform itself is continuous function of omega. Okay. Fact 2 is that DTFT is periodic in omega with period 2 pi. And the way to see that is very simple. You look at the definition of x of e to the j omega. It's minus infinity to infinity x of n e to the minus j omega n. Now replace omega by some multiple of 2 pi. So let's say I want to compute x of e to the j omega plus 2 pi k. Well, I plug that into the formula. X of n e to the minus j omega plus 2 pi k n. I expand that. Xn e to the minus j omega n e to the minus j 2 pi kn. Right? Now this is something that will come up again and again, that you can check it using Euler's identity, but e to the j 2 pi kn is simply 1. So what you are left with is n x of n e to the minus j omega n, that is equal to x of e to the j omega. Right? So this is of course to be expected because we already talked about the discrete time frequencies being non-unique. The discrete time frequencies are primarily from minus pi to pi, and then after that they just repeat themselves. So what this is saying is that if you were to look at the DTFT x of e to the j omega, it is enough to focus on any 2 pi long region of omega. Yeah. And in general, we say that we'll just primarily look at omega from minus pi to pi. Because after that, whatever is the Fourier transform, it will just keep on repeating itself. Now, previously we looked at absolute values of the discrete time Fourier transform. Let's look at some other interpretations of how do you look at a Fourier transform and make some conclusions about the signal. So right now I'll focus only on the magnitude of the Fourier transform. So let's say that someone gives you a signal, you compute its Fourier transform, and then you plot its discrete time Fourier transform, and it looks like the following. So this is minus pi, this is pi, this is pi by 2, minus pi by 2, pi by 2. And because of the periodicity, as we talked about, this thing will just repeat itself after that. And so forth. These bumps will keep on repeating themselves. Now, if you look at this signal, as we talked about earlier, we said frequencies around 0 are low frequencies and frequencies around pi are high frequencies. So the interpretation of this signal is then you say that this signal has mostly low frequencies and not that many high frequencies. So you have a Fourier transform which is really has high values around low frequencies. So this is sort of like a signal with mostly low frequencies. On the other hand, someone could give me a Fourier signal whose Fourier transform's magnitude looks sort of a negation of this. So this is 0. And this is minus pi, this is pi. And it could look something like this. Supposed to be. And then it will repeat itself. So, and let's say that this is minus pi by 2 and this is pi by 2. My drawing is not up to scale, but you get the idea. Now, if you look at the Fourier transform of this signal, what do you say? You say that this signal, unlike the previous signal, the signal xn has mostly high frequencies, because we already talked about in discrete world, frequencies around pi are the high frequencies. So this is a signal which has mostly high frequencies. So far we have been talking about abstract plots and abstract values. Let's take a look at explicit examples. So an example, the first example is simplest signal x of n equal to delta of n, which is called the Kronecker delta. Right? Hopefully everyone remembers the definition of delta of n, which means that it is 0 for n equal to 0. It is 1 for n equal to 0 and 0 for all other values of n. If I plot it, it looks like this. N equal to 0 and it's 0 otherwise. So here is a signal which is 0. All of a sudden it becomes 1 and then it becomes 0 again. So there is an intuitive understanding of that this is a signal which is really like changing very, very, very rapidly, right? But it's 0, becomes 1, becomes 0 again. What kind of frequencies are present in the signal? We can always use the Fourier transform formula and we will do that, but intuitively you could try to guess which frequencies are present in this. Intuitively, this signal contains all the frequencies that can be there at the same contribution, just like the continuous time delta. Now we can verify that by simply doing the formula. So the Fourier transform of delta of n, that's x of e to the j omega. We compute that summation n from minus infinity to infinity, delta of n, e to the minus j omega n of this whole thing, right, is 0 for all n. So since delta n is equal to 0 for all n except n equal to 0, so we get this whole summation goes to 0 except for n equal to 0. So for n equal to 0, I get e to the minus j omega 0, which is equal to 1. So if I look at the Fourier transform, it's x of e to the j omega. It looks like this. It's a constant for all values of little omega. Right? Minus pi, and it keeps on going. So what it tells me is that a delta function contains all possible frequencies in the discrete time realm, just like the delta function in the continuous time world. Okay, let's look at another example. So this is example 3.6 in your text. So your x of n equals to alpha to the power n u of n. And alpha can be a complex number, but absolute value of alpha is less than 1. So let's just first compute x of e to the j omega using the formula. I get n from minus infinity to infinity, alpha n un e to the minus j omega n. So un is the unit step, so everything before 0 goes to 0. So I have the summation left from n equal to 0 to infinity, alpha n e to the minus j omega n. Okay. Or I can write that as n from 0 to infinity, alpha e to the minus j omega whole power n. Now how do we solve that? So we can use the geometrics sum formula, n from 0 to infinity. We know r to the n equals to 1 over 1 minus r if absolute value of r is less than 1. Now in our case, r is equal to alpha e to the minus j omega. Right? So this is our r. So we check first what is the absolute value of that. The absolute value of that is simply the absolute value of alpha, and we are given that that is less than 1. So the answer will be 1 over 1 minus alpha e to the minus j omega. Right? So that's our Fourier transform. Now, this is really hard to say what will it look like. So what do? We'll do some plotting of this for different values of alpha in MATLAB to get an understanding of what do these things mean. So here is an example. I just want to remind you that we were given xn equal to alpha to the n un, and the requirement was absolute value of alpha is less than 1, and we computed x of e to the j omega equal to 1 over 1 minus alpha e to the minus j omega. So let's take a look at it. Here is a little script. You can go and plot, do it yourself. This is my definition of x, and I wrote a function where you could put in any value of alpha, right? And then this just plots the Fourier transform magnitude and phase of my Fourier transform. So let's look at what happens if I use alpha equal to 0.9. So this is what my xn looks like. This is my xn. Of course, it starts at 0. Now, if I am, the closer my alpha is to 1, the slowly this signal will decay, right? Now, intuitively, if something is decaying very slowly, is it changing fast or slow? It's changing slow. So you expect a signal that is changing slowly will have mostly low frequencies. A slow changing signal will have mostly low frequencies, right? So if I plot, this is the absolute value of x of e to the j omega, and this is the phase of x of e to the j omega. And this is minus pi, and this is pi. Of course, Fourier transform is periodic, so you see the peaks again. So what do you see? That this signal has mostly low frequencies, right? Because it's decaying very slowly. But of course, if I just show you one picture, it will be hard to understand that part. So let's compare it with the case where alpha is equal to 0.1. So now my alpha is very small. So what's happening now? My signal is rapidly going to 0. Previously alpha was 0.9, it's slowly going to 0, now it's going to rapidly go to 0. Let's take a look at how does it look, right? Look at this. This is my xn, right? Because it's 0.1, it started at, of course, no matter what value of alpha, at n equal to 0, you will be 1. But then it rapidly goes to 0. So what do we expect now? What kind of a Fourier transform do we expect now? A signal which is rapidly changing will have more high frequencies or less high frequencies. Previously, we saw that this is the shape of the Fourier transform here, right? And the envelope is very much concentrated around 0. What will we expect now? That the envelope will actually expand. It will now have more higher frequencies also. Okay? So indeed, if I do the plot, this is what you see. This is my absolute value of x of e to the j omega. This is minus pi. This is pi. And you see that now I have all these frequencies present because my signal is rapidly going to 0. And if I were to actually make alpha really small, then I'm actually approaching delta, right? And what is going to happen? This envelope around 0 is going to keep on getting bigger and bigger and expanding. Eventually it becomes a flat line. It includes all possible frequencies. So while we were able to calculate the discrete time Fourier transform, that wasn't enough. It's really important to understand what is that Fourier transform telling me. What is the intuition behind my Fourier transform formula? And if I just take a look at the signal, what will I expect to see in the Fourier transform? The phase plot tells you that how late a frequency starts from the other. So a phase is just a meaning, and we'll talk about it more, but a phase plot doesn't, of course, tell you how much frequency is present. That is given by the magnitude plot. The phase plot tells you how late a frequency is starting, right? So you can have cosine of, for example, cosine of something. Now I can add phase. What does that do to the cosine plot? It shifts the cosine, right? If you shift cosine by pi by 2, what do you get? You effectively get sine. So the phase plot tells you what is the starting point of different frequencies in relation to each other. Okay? If the phase plot is non-zero, that means that not all the frequencies are starting at exactly the same time, right? And it is through the combination of those frequencies that you end up getting the signal that you were looking at, which is not periodic at all.